Okay, I think we can start. Well, welcome. Thank you for coming to Functional Programming and Clojure. This talk is called Fundamentals of Functional Programming, but we're going to do it through the prism of Clojure. My name is Ronen Cohen. I'm a tech lead at AppsFlyer. We're a large Clojure workshop. AppsFlyer is a company who does mobile analytics and attribution. We ingest in excess of 90 billion events every day. We have a lot of, we have 70,000 clients and 700 employees, but more interestingly, perhaps to you guys, is that we ingest 90 billion events every day, and we do it primarily with Clojure. So Clojure holds all the pipeline that allows us to receive this traffic of 90 billion events every day. And chances are, if you have a smartphone, which I'm guessing everybody does, is that you have the AppsFlyer SDK, because we have 70,000 clients, and most likely some of the apps on your phone have this our SDK installed in it. Okay, so Clojure. Why are we here to talk about Clojure? And what is Clojure? Clojure is a programming language. It's a Lisp. Like if you've ever used languages like Common Lisp or Scheme, Clojure is one of the, it's in this family of languages called Lisp. It's a functional language. It's performant. It can achieve a performance that's on par with Java application written in pure Java. And it runs on the JVM, which means that you have access to the entire ecosystem of the JVM itself, and any other open source library or framework that you might want to use. So it's all there. You can still use that. Any of the libraries or frameworks that you like to use, they're accessible through Clojure, and they're accessible easily as well. And what's interesting about Clojure is that it was oriented from the beginning, when it was designed by Rich Hickey, the author of Clojure. It was designed to make concurrent and parallel code simple to write. So I'm sure you all know some of the problems with some of the difficult parts of writing concurrent and parallel programs, right? You have mutable state, which means you need to have locking mechanisms and concurrency primitives to achieve that, which is, it's difficult. So what Clojure does, it takes a different philosophy in which data and state is immutable by default, meaning that you cannot change data. You can apply a transformation to it. For example, you can add something to a list, but the data itself remains the same as it was before. So this eliminates a whole class of concurrency and parallelism issues that you would need to deal with by using locks or other concurrency primitives that you're used to from writing maybe Java or some other programming languages. A little bit about the history of Clojure. So 1958, Lisp was invented, I think, in MIT by a very smart man called John McCarthy. Back then, they were using Lisp a lot for AI. And from that first Lisp, later on came other languages such as Common Lisp and Scheme, Emacs Lisp, which is a Lisp dialect that is used when developing Emacs. In 2007, Clojure was invented by Rich Hickey. He wanted a Lisp. He liked Lisp. I think he was using Common Lisp, and he liked that. And he had some problems with Java. For example, mutable state. And he wanted a language that would be a Lisp and would support the notion, for example, of immutable data, and also would be a practical language, right? Because he wanted, for example, to be able to run in a JVM, because the JVM has been around for a very long time, and it's an incredible runtime, and he wanted to be able to keep using that. So From the beginning, he geared it towards running on the JVM. Clojure compiles to bytecode, in fact, so it just runs on the JVM natively. And in 2011, there's actually a new language called Clojure. Well, it's not new, but since 2011, it's a language called ClojureScript, which is Clojure, and it runs in the browser. So you can write, you can use it instead of JavaScript to write web apps in the browser. So a little bit about functional programming and what we mean by that. I mean, I'm sure maybe some of you have used functional programming or heard about functional programming. Today, it's very prevalent. A lot of notions and ideas from functional programming exist in a lot of ecosystems. Newer versions of Java have lambdas and they have streams. These are ideas that were taken from other functional languages. So maybe you were familiar with some of these ideas. But just to take, I mean, and functional programming can mean a lot of different things. You have, has anyone here ever used a functional programming language? Not so much. You did, yeah, of course. So it's like a spectrum, right? You have languages that are purely functional, like Haskell and OCaml, and you have languages like Clojure, which are not purely functional languages, but they still support. But they're still functional. And if I had to sort of, choose a few things in Clojure and describe why it is a functional language, it would be these. The functions are first-class citizens, meaning you can pass them around. You can take a function and send it as an argument to another function, or return a function from another function. So they're just like anything else in your language and like any other type. Data is a first-class citizen, and we'll get to that a little bit later, but it just means that we model our domains using data structures, native Clojure data structures like lists and maps and vectors. That data is immutable. That's what we spoke briefly about before, that you cannot change data. Data is a value, and it cannot be changed. You can apply a transformation to it and receive new data, but the original one stays as it was. And that programs are basically pipelines of functions. You write lots of small functions that receive some data and return some other data, and then you compose those small functions together towards bigger functions that solve a bigger problem. Okay, so that's basically the introduction. And how this presentation is going to work? Oh, I think my screen, hold on. Nope. Okay. How it's going to work, I'm going to basically be live coding with you and show you examples on the screen. What you're seeing here is Emacs. The left side of the screen is a Clojure file, and the right side of the screen is a REPL. And you should be able, if you installed Cursive or Emacs, you should be able to spin a REPL up now. Or you can just follow along with me. I'm going to show you examples. Introduce you to Clojure. This is going to be basically like a small introduction to Clojure and some of the ideas behind Clojure. And there's going to be an exercise as we go along for you to do some live coding. Okay, so can everyone see the screen? Is this big enough? Not big enough? Okay, 1 second. Is better? Okay. Is this okay? Cool. So let's talk about Clojure. Let's see what the language is made up of. So I said the left side on the screen is a Clojure file. You can open this right now if with whatever editor you installed previously. And each Clojure file holds a namespace. Okay, this is a namespace called devoxx19.core. Okay, you can sort of think of it as a class file. It's not really this. It's not an exact analogy, but you can think of it this way. And a namespace holds definitions. Definition can be some some global data structure, functions, and stuff like that. Okay, so let's talk about the most atomic things in Clojure. So we have integers. If I take this and I put this in the REPL, the number 42, we get a 42. And if we take the type of 42, then you see it's a Java lang long. Okay, firstly, it's a Java object, obviously, because we're running on the JVM. But furthermore, it's a regular Java long. Okay, a boxed long. Okay, and same goes for doubles. If I evaluate this number in the REPL, I get back a double. I can check the type of it, and it's a double. And one of the things that I kind of want to illustrate during this talk is the way that we develop Clojure. So what you're going to be seeing me do a lot is type some code in the left side. It's mostly already typed, but define something on the left side and then push it to the right side, to the REPL, to evaluate. And this is sort of how we write code in Clojure in this very interactive way, where we define a function, and then we just go to the REPL and we can try it out, we can invoke it, we can see that it works the way we meant, and then move on to define some other function, then keep sort of experimenting in the REPL. It's a very interactive way of doing this, of doing things, as opposed to maybe some other methodologies, such as, like, when I wrote in Java, I'd usually I would have some code, and I would type some stuff in, and I would run maybe some unit test. But then, to make sure that it works, I would have to actually hit play, like an IntelliJ, hit run, and see what happens. And it might work, or it might crash, throw an exception, I don't know. And then I would have to go back to my code and fix it, and figure out, oh, this is wrong, this is this. And I could just keep doing this iteratively over and over until I had what I wanted. But in Clojure, you're constantly interacting with your code, with your system, right? It's always there. You don't have to stop and start and stop and start. You're just doing it interactively, which is one of the things I like the most about Clojure. It makes for a very, in my opinion, for a very productive way of developing and writing code. Okay. So we saw integers and doubles, and we also have booleans. Not much there. You have true and you have false, and they're pretty much what you'd imagine they are. Whoops, I'm sorry. If I type the type of false, I get a boxed Java boolean. There's no surprises there. Strings are regular Java strings. They're Java lang string. Hi everyone. Java lang string. And then we have symbols, which are a special construct in Clojure. It's not something that exists natively in Java. They're a special construct. We're not going to talk about those much. And we have keywords. And keywords are interesting because keywords basically they evaluate to themselves. Keywords are mostly used in Clojure as, for example, keys in maps. So we can write an expression like this. I'm going to define a map. I'm going to have the key Devoxx, and the value will be the string Ukraine. Okay, so keys are most often seen in stuff like maps. Okay, so that's the basics. That's like the atomic data structure, data types in Clojure. And then to build on top of those, we have Clojure data structures. So first, we're going to see lists. Lists are like linked lists. You can think of them as singly linked lists. Okay, they're defined this way with round parentheses, and they grow at the start. So when you add a new element to a linked list, it will be added to the start. So for example, I'm going to be calling a function called conj. I'm going to pass it a linked list and some number to add to the list. and it's going to be added at the beginning. And the first thing that you might appear strange to you when you're seeing this code for the first time is the syntax, right? I told you conj is a function, and this is basically the syntax of Clojure for invoking a function. You have you open parentheses. The function is the first element in that list, and what comes after are the arguments. Okay, so this might seem a little foreign to you, but this is basically the syntax of Clojure. It's basically syntax. It's Lisp syntax. If you've ever seen other Lisps, this is pretty much what it looks like. Okay, so except for lists, we have vectors. You can sort of think of vectors as arrays. Vectors give us random access, unlike lists. In list, if you want the nth element, you have to traverse the list. So it's a big O of n. Vectors give us random access. It's not exact random access because they're not actual arrays. Inside Clojure, they're represented as trees. All of these data structures, lists and vectors and maps, are persistent data structures. Persistent data structures means that they're immutable. And the implementation that Clojure takes is representing them as sort of trees. So it's not random access, but it's close to being random access. Okay. I don't want to talk about that too much because that's just going to take up too much time. I just want to keep going and show you the rest of this. So unlike lists, vectors grow at the end, right? So if we're going to call conj like before, which adds a new element, if we're gonna run this at the REPL, what are we gonna get? Someone want to say? What's good? Yes, right. Because they're arrays; they keep growing at the end. Very good job. Then after that, we have sets, which you can think of as hash sets. Okay. And maps, which we've seen just a second ago. This is the syntax for them. This is a map literal. You open squiggly brackets, and then it's just a list of pairs. Okay, we have a key A and the value 1, and then a key B and the value 2, and so on. And that's basically it. Those are the fundamental data structures in Clojure, and they nest. Okay, so you can nest them within each other. For like in this example, where we're going to define a vector whose first element is a list, and its second element is some set, which holds the string hello. So all of these nest, and you can compose them together. So we mentioned immutability and persistent data structures briefly. And I want to show you an example. So what we're going to do is we're going to define some variable called myList, and it's going to hold a value that's a list of the numbers 1 to 3. Def is the way that we define, for example, like variables and so on. And what I'm going to do is I'm going to call the function conj and add a new number to the list, number 4. So we started out with a list of 1, 2, 3. We added a number. We got back 4, 1, 2, 3 because lists grow in the beginning. But what do you think happened? What would you expect to have happened to the original list? Nothing, right? Because it's immutable. So if we inspect the original list, if we just evaluate it, we see that we got back 1, 2, 3. And this is important, right? Because this illustrates the idea of immutability in Clojure. The data itself cannot change. Data is a value, and you cannot change it, but you can apply a function to it to get something back instead of to get something back new. I'm sorry. Okay? And the reason, why do you think this is important? What is the point of this? One point would be, for example, concurrent parallel code, right? If this were immutable, meaning if when I called conj I would be changing the list, then if this piece of code would be running from different threads, then I would have to somehow protect this data from concurrent access, right? With Clojure, that is something that I don't need to do because data is by default immutable. Okay. And similarly, I'll just show you another example. If I'm going to define a map that has 3 keys, A, B, and C, and I'm going to call the function assoc. Assoc is a function that takes a map, and it takes a key and a value, and it adds that key and the value to the map. If I'm going to call this, then I get back a new map, now with D assoc to the map. But the original map, my map that we defined, is left unchanged. So immutability, like I said, it eliminates a class of concurrency problems, but maybe more interestingly to you right now, if just so you understand a little bit about Clojure, it also makes our code easier to reason about. Because imagine, do you guys write in Java? Okay, so in Java, when I used to write in Java, I would be writing code and I would always have to have this concern in my head. I would define a method or I would invoke another method that would receive some arguments, and I would always have to think, okay, I'm gonna send this object to the method, and I need to be certain that this method or the other method that this method might invoke later on, this graph of methods, does not change my object. Or maybe it does change it, maybe I'm okay with it, but I always need to know that the arguments that I'm passing on, I need to know if they're gonna be mutated or modified. So I have this underlying concern in my head the entire time while I'm coding. With Clojure, it's something that does not exist. It's something that I never, ever have to think of because data is immutable by default. So I know that if I'm sending an object, in this case, some data structure like a map or a list to a function, I know that it cannot change it. It might transform it and give me back a new something, but the original something does not change. So this is nice because it makes our code easier to reason about because it's one more thing that we don't have to be cognizant of as we're coding. And by the way, it's a workshop, so if anyone wants to ask a question, interrupt me, just feel free, please. If anyone has a question, just go ahead. Anyone? Okay. Yes. Mm-hmm. It is a very good question. Yes, so maybe some of you are thinking, this is nice, but it seems terribly inefficient because maybe what conj is doing, it copies the entire thing, it like clones it, and then adds the element to the list. But Clojure uses something called persistent data structures. I mentioned them briefly, in which there's structural sharing. So you're not, whenever you're adding something to a list and getting back a new list, or adding something to a map and getting back a new map, whatever, you're not copying everything and then adding. You don't have 2 copies in memory of the entire map. Basically, the new map and the old map share most of their structure except for that little something that you added or removed or whatever, okay? So memory-wise, it is much more efficient than cloning everything all the time. Okay, that's a good question. Any other question? Yes? Yes. They're allocated on the heap. It's a regular Java allocation behind, behind. I mean, it's subject to everything else that you would expect from a Java program. Allocation, the memory model works the same. Escape analysis works the same. It's all there. Yes.
There are no simple types.
You mean primitives? Are you asking that because when I showed you that it's boxed? Okay. You can still use primitives in Clojure. You just need to be careful when you're doing it. It's not something that we're going to discuss. Basically, you can still use them, but imagine that you have a primitive integer, and you want to pass that as an argument to a function. So you need to use type hints. It's not something that we're going to cover, but you need to type hint the function, type hint the argument on the receiving function that says, okay, this is a primitive int, because otherwise it's going to just box it. So you can still use that. You just need to be careful. You just need to know where you're using them and how to type hint the proper functions. Any more questions?
Also, when we started those examples, integer wasn't actually not the integer type, but
it was
long.
Boxed. Yeah.
It was long. I mean,
oh yeah, so it uses long, but you can still use integers. You can still, it just by default, it defaults to longs, not integers.
Okay.
But you can still use any primitive types that you're used to from Java. It's all there. You just need to be careful sometimes. And sometimes you might need, for example, if you want to do some primitive arithmetic, as Clojure supplies special arithmetic functions for a primitive arithmetic. You have a question?
I have another small question.
Okay.
Maybe it's not quite small. What are the differences, global differences between Clojure and common Lisp?
There are a lot of differences, and I'm not a common Lisp person, so I'm maybe not the best person to ask. But from my small experience with common Lisp, firstly, common Lisp has lots of distributions, and it has SBCL and all these things. Clojure pretty much runs on the JVM. Common Lisp is not functional by default, if I'm not mistaken. It's not immutable by default, if I'm not mistaken. Again, I'm not sure. Common Lisp has the whole class thing, the Common Lisp object system, I believe it's called, for object-oriented programming, which does not exist in Clojure at all. It takes very many different approaches from Common Lisp and lots of different things. Clojure comes with concurrency primitives that do not come with Lisp. It's a whole other language. But I've never really coded in Common Lisp beyond just some, just for a little bit of fun. I'm not sure.
Me too. Thank you.
Yeah. Okay. The macro system is similar, I believe. Okay, so functions. So we saw the atomic data types like numbers and strings. We saw data structures, and now I want to show you a function. And over here, can you guys see? I'll make it a little more centered. Where this is syntax for defining a function. So over here, we're defining an anonymous function, like a lambda, that receives 3 arguments and it just ignores the 3rd argument, and then it just adds the first 2 and multiplies by 5. Does everyone understand what this function is doing? Do you understand the syntax? You have to remember that in Lisp and in Clojure, the function, when you want to invoke a function, it's prefix notation. So the function comes first, and then the argument. So what we're doing here is we're taking x and y, and we're adding them. We're calling plus and then x and y. And then that expression is evaluated and passed on to the surrounding expression in which we multiply that expression by 5. Okay, does that make sense? It's a little hard to get used to at first. So we need to kind of pass that hurdle to keep going. Any questions? Okay, cool. So here we defined a function. If I send it to the REPL, then I get back a function with some weird name, doesn't really matter. And if I wanted to invoke that function, I could do this, for example. So what's happening here? It's an anonymous function, right? So we surround the anonymous function with new parentheses, and then we send it arguments 0 and 1. And we get back 5. Does this make sense to everybody? Okay. That's not how we usually write functions. We don't constantly, define new functions and then just sort of invoke them right at that spot. What we usually do is we want to be able to give our functions a name. So to do that, we use something called defn, define function. So here we're defining a new function that is equivalent. It's not equivalent because it takes 2 arguments, doesn't matter. It's equivalent pretty much to the previous example. We define a function called foo, takes 2 arguments. It's this thing, this vector of symbols, and then some expression that we can use our arguments with. Okay? The function can use the arguments within its scope. And if we wanted to invoke it, we would just call foo with some numbers and get back the number 5, I guess. Questions?
What is the difference between def and defn? Like it looks similar.
Def and defn?
We can define the variable and set lambda.
Yes, you can do that. Defn, I'm going to be mentioning the word macros, just ignore it. Defn is a macro that expands to def and then a lambda. It's the same. Def is a construct to define, to define something called a var. Like a var can hold some piece of data or reference something like a function or a list or whatever. Defn just expands to def, name, and then the function.
So this is just a different syntax?
Yeah, it's just for easier. So you don't have to you don't have to write fn all the time. Yes?
To avoid class cast exception.
You can define, yes. It's similar to the question that was asked before about primitives. You can type hint the arguments. Okay, you sometimes use that to. Imagine that you're passing some Java object to a function like a string builder, and inside I didn't show you yet, but I'll show you a little later. And then inside the function, you do want to call a method like append. Well, Clojure compiler does not know that what you passed it from some other context is a string builder. So you need to. So what it has to do by default is do reflection, right? Basically, it says, "Oh, you're calling the function append. I'm not sure what the type that you're invoking on is. So I'm just going to do reflection. I'm going to find the method append and then call it that way, which is performance-wise, it's really bad. So you can use type hints to tell the Clojure compiler, oh, this thing that this function is receiving is in fact a string builder. You don't have to do reflection, just call append on the string builder. You had a question?
Yes. Is there any specific reason for using the prefix notation for operators?
Yes. Well, firstly, because it's Lisp, and that's Lisp syntax. The more deep answer would be that this allows us to basically, if you think about it for a second, what you're seeing when if you're looking at a definition like this of def and foo blah blah blah, you can look at it and say, oh, he's defining a function. Or you could look at it and say, he's defining a list. His first element is a symbol called defn, his second element is foo, third element is some vector, and then so on and so on. It's just a nested recursive list structure. And what this allows is, when you have this equivalence between the syntax of your language, the code, to the data structures, when they're equivalent, this allows you, this is something called homoiconicity, and what this allows you to do is something very powerful called macros in Lisp. Basically, it allows you to write functions that work in compile time. It's not exactly in Clojure, it's a little more complicated than that, but we can write functions that work in compile time that take code, and because this code is the same as data, there's an equivalence there, because the syntax is just lists. Everything is a list. It allows you to write these functions that receive code and return new code. So it allows you a very, it gives you powerful meta-programming facilities. It's a very good question, but I have to spend 2 hours just talking about that. But yeah, it's an interesting question. Anything else? Yes.
Yes, thank you. I want to ask about that in first function, where we use it.
I'm sorry, I couldn't hear you.
That first function, argument, certain argument, that.
Here?
No. Highest.
Z?
Yeah.
That's my fault. I should have removed that. I forgot. Actually, Emacs is nice enough to warn me. I don't know if you see, he's saying this is not, you shouldn't be doing that. It's an unused variable, but I ignored it.
Thank you.
Sorry about that. Should have been clearer. Okay, so we talked about functions. Now let's talk about pure functions. What are pure functions? Basically, pure function is this sort of definition that functional programmers like to talk about. And basically, it just means a pure function is a function that given, if you invoke it twice with the same arguments 2 times, it's going to return the exact same thing. Okay? You sort of can think about it in a mathematical way. It's sort of like a mathematical function, right? A mathematical function, if you call a sine function and you pass it some number, you're not going to get 1 time and 0 the next time. You're always guaranteed to get the same thing. We don't even think about it. It's like at the definition of mathematics. So pure functions, if you call it twice, if you invoke them twice, give them the same arguments, you're going to get back the same thing. And what that basically means that you cannot do side effects, right? And the word side effects can mean you cannot do any sort of I/O. You cannot go to the network. You cannot go to the file. You cannot do the file system. You cannot talk to any devices. You cannot rely on any type of randomness or the notion of time, because if you rely on randomness or the notion of time, time passes. So you might get different results if you call the function, if you invoke it twice with the same arguments. And similarly, there's no dependence on state, on global state, because global state changes with time, right? Global state might not be static, it might change. So if you rely on state, if your calculation relies on state, then and the state changes, then your result will change as well. So pure functions, just to simplify, they're just functions that do some sort of calculation on their arguments without talking to any devices, without doing any type of randomness, without relying on state. Like this function, like the function that we defined just a second ago, where was it? This one. This is a pure function because all it needs to know for it to function are its arguments, x and y, right? It doesn't do anything else. So these are pure functions. And the reason that we even talk about pure functions is that pure functions are, firstly, they're very simple to reason about. If all you need to know, if your function is basically a sort of like a black box that you plug in arguments from one end and get back something out the other, and if you think about functions that way, then pure functions are very simple to reason about because you know what they're going to do. If you're invoking them, you know for sure what they're going to do because you know what arguments you're passing. So they cannot surprise you, right? They cannot change whatever they're returning from one invocation to the other. So they're very easy to reason about. You just need to know whatever expression is in here, right? That's all you have to know how they work. You don't need to know what time it is. You don't need to know what the state of the, your file system is, or any other device, or any of that. Just whatever you expressed as the function. For the exact same reason, they're very simple to test, because if you know the arguments, you know what you're going to get. So they're very easy to write tests for. They're parallelizable because they're not trivial to parallelize necessarily, but they eliminate a class of issues that you'd have to think in order to parallelize them, such as access to the disk, access to the network, mutation of global state. Those are concerns that you don't need to occupy yourself with just because, by definition, they're not going to deal with those things. And lastly, they're composable, and what that means is that you can easily take two functions and compose them into a bigger function. By composition, I mean, imagine you have two functions, so you can write a new function that is the composition of them. When you invoke them and pass it an argument, it's going to call the first function in the composition, get back something, and use that to pass that to the second function. That's what we mean by composition. Any questions about this? Yes.
So how to write a program that does something useful? I mean, access network, files.
That's a very good question. So I mentioned briefly in the beginning that functional languages are sort of on a spectrum. And on the far spectrum of the far side of the spectrum, you have languages like Haskell that are purely functional. And what that means is that you can only write pure functions with them. So then, like, how do you use them? That's for those we use things like monads and other ideas from type theory and category theory. But I don't want to talk about those. We'll talk about Clojure. Clojure is not a purely functional language. We usually, when we code, we define our functions as pure functions, but we usually have on the edges of our system, you write a lot of pure functions, and then you compose them towards this pipeline that defines your program. So code comes, data comes from one end, goes to one function, calls some other function, and so on, and so on, and so on, and then you get something from the other side of the pipeline. Usually on the edges of our system, we would have some functions that do side effects, like read from the network or open a file or something. So Clojure does not force us to write in a purely functional way. We do have reliance on state because we need those to write programs that are useful and actually do something. But it's more of a question of how we sort of build up these programs, right? So we have a lot of intermediate pure functions, and then on the sides, you do some calculation, then you need to do something with it. You might want to write it to the network or open a socket or whatever. On the sides, you would have this sort of side effect. Okay. Any other questions? No. Okay. Okay. So, what else can we do with functions? I mentioned that that functions are first-class citizens. So they're no different than any other thing, any other type in the language. Like other types, you can return them from functions. So here we're defining a function called foo. We're redefining the previous function. Foo, if you take a look, the previous function that we had over here took two arguments and then it added them together, it summed them up and then multiplied by 5. Over here, we're redefining foo only takes an x, but instead of returning whatever it was returning before, it returns a function that receives y. And that function will do the calculation. What this is showing you is that functions can be returned from other functions. Does this make sense? Do you understand? Okay, so like if we wanted to actually use this, let's see what would happen. So if I invoked foo with a number 0, what would I get? Anyone want to say? What would be the type of whatever was returned from this function, right? Because I did not define it. 1 second. So redefine foo. 1 second. Okay, yeah. I redefined foo, called it, got back a function. If I wanted to call that function, I would have to do something like this. So now I get back 5, right? Because I wrapped the function that I received inside parentheses and invoked it as a function with y this time. X is here, y is here. Similarly to that, we can pass functions to other functions. So here we're defining a new function called myOdd. It's basically a function that takes a number and tells you if that number is even or odd, if it's odd, true, if it's even, false. But the interesting thing here is, firstly, notice that it's not relates to your question. We're defining a function without def n. We're just using def some name, myOdd. We're going to give it, and the value is whatever is returned from this expression, complement even. And complement returns a function, and it receives a function. Even question mark is a function that tells you if a number is even. And what complement does, it returns you a function that when you invoke it, it actually invokes the function that you gave it, even, and just returns the opposite. So if even returned true, I'll get back false, right? So this way, we just defined a function called myOdd, right? Because it's just going to return the opposite value for even. So complement here is receiving a function which illustrates that functions can be received as arguments as well. Any questions about that? Okay. Okay, so next thing I want to talk about are higher order functions. Higher order functions, higher order functions are basically functions that receive functions or return functions. Okay, that's a very informal definition, but you can think of it this way. So for example, complement is a higher order function because it receives a function. And what higher order functions allows us to do is write other functions that receive functions and some, for example, some data structures, and the receiving function acts as sort of like a recipe for what we want to do. So the function map, I'm going to show you an example before proceeding. I'm going to invoke the function map. Map is a function which takes a collection, like the numbers 1, 2, 3, and a function. Inc is a function for incrementing a number. And what map does, it returns us a new list, a new collection, in which the function is applied to every element in the original collection. So anyone wants to guess what this is going to return? Sorry? 2, 3, 4. Yes. 2, 3, 4, right? It just basically, it took the collection and applied the function to each element. And you can think of map as sort of this abstraction for modifying a collection, right? Usually in imperative languages like Java, maybe in newer Javas you would not be doing this, but basically you would code this with a for loop, right? You would have some for loop that goes through the numbers, and each time calls increment and appends it to a new list and then returns it. Map acts as a sort of basic abstraction for transforming a list. We could pass any function that we wanted to here. We could pass a function for doubling or whatever, and map would take care of the mechanics. So we don't care about the mechanics. We don't care about the traversal of the list. We don't care about applying the function. We don't care about creating a new list in the beginning and appending to it. Map does that for us, right? We just need to express whatever. This allows us just to express whatever we want. We just express the logic that we want to apply. Okay. And similarly, you know, there's functions like filter. Filter is also, I'll show you in the REPL, filter, even 1, 2, 3, 4. Filter goes through the collection and filters out whatever, well, only keeps the elements for which the predicate, we pass as a predicate, even, question mark, only keeps the elements that the predicate returned true for. Okay? And similarly, the idea again is that we didn't have to worry about the mechanics. We just had to use this abstraction for filtering a list, right? In imperative languages, again, we would traverse the list with some for loop, and then we would check like if this is even, and then append, otherwise we wouldn't do anything. Filter does this for us. And the nice thing is that these are composable, right? Like I could write this and compose these two transformations together, and this composition expresses exactly the logic that I'm interested in. It expresses that I want to go through a list, increment them, and then filter them. There's no mechanics involved on my end, just the expression of the logic. Enclosure, actually, if you keep composing these two together, it gets really hard to read, because imagine that you had more and more filters and maps, so we would have to be very nested. So Clojure does provide us a way for expressing this in a more elegant and easier to read way via something called a threading macro, in which we just write this double arrow, and you can think of it as it takes, like you start with an initial value, you pass it to the first expression, and that expression moves on to the second expression, and that moves on to the third expression. So this is much easier to read. It's easier to read mostly because it reads top to bottom instead of, you know, in this nested way. So this just, for example, this increments the numbers, then it filters them out, then it does this mapping transformation of multiplying them by 3. Any questions? No questions for this? Okay. More things that are functions. Maps are functions. Maps are functions of their arguments. For example, we could invoke a map as a function. The argument would be a key, and the function returns returns the value for that key in the map, or null otherwise. I didn't actually mention this, and it's important. Null exists in Clojure. It's the same null as in Java, except in Clojure it's called nil. So nil is the same as null. Also, keywords are functions. Keywords are functions in the sense that if you give them a map, they will return their own value in the map. So here I'm using the keyword A, passing it some map, and getting back a 1, because that's the value of that keyword in the map. Is this understandable? Yeah. Okay, so I want to talk for a second about sequences. So sequence in Clojure is sequence is like one of the most important Clojure abstractions. Basically, you can think of sequences as representing a logical list that you traverse sequentially. And basically, sequences are something that you can always inspect the first element of that sequence, and you can always get back the remaining values, the remaining sequence, everything after the first. So the functions first, rest, and cons are functions that sort of define a sequence. So first of a vector can be turned into a sequence. So if we call first on a vector, we get back 1, and if we call rest on a vector, we get back 2 and 3. And cons is a function. It's not conj. We saw conj before, but this one is called cons. Cons is a function for building up new sequences. We're going to get to like why we're using this in a second. So cons, for example, if it receives a sequence and some number, it adds it at the beginning, always. No matter if we passed it a list or a vector or some other type of sequence, it's always in the beginning of the sequence. Okay. Like you can see, I added 4, it goes in the beginning. Okay. Maps, most closures, the data structures that we saw before can be made a sequence. So for example, even things that are not obviously, that it doesn't usually mean, it's not obvious that they would be able to do that. For example, we can call rest on a map. And maps don't usually have any predefined order, right? Hash maps. But maps, when you turn them into a sequence, they're just a sequence of pairs, keys and values in some order. And if we call rest on this map, I don't know what we're going to get. I'm guessing, yeah, a new sequence. Rest returns us a new sequence of tuples, B2, C3. Okay, that's pretty much the bare definition of sequences. And the reason that we're talking about sequences is because Clojure has a very rich sequence library. We saw map and filter, but the core of Clojure, the core of the Clojure standard library are a lot of functions that deal with sequences, that receive sequences and return sequences, and this allows us to use sequences as general purpose data structures, and you keep using the same abstractions to define our logic on them, like map, filter. Question? Yeah.
So I have a question about this rest
Yeah.
method.
Yeah.
So in the case of hash map, it returns always the same. I mean, key values will be in the same order whenever I call the rest method.
I'm not sure I understand. I follow the...
So, I mean, map becomes a sequence, right?
Yeah.
So the elements in the sequence always like transform and becomes in the same order whenever
yes,
I
but
make it a sequence.
For the same map, yeah, they will be in the same order. Yeah, yeah.
But if I like add one key, it can reorder everything.
I'm not sure in the case of map. It's a good question, but I'm not sure because I think so, but I'm not sure. I'm not sure. But maps, usually the order is sort of undefined, right? So sequentializing them is also undefined. It's more of an example of, showing that everything can be thought of as a map. If you want order, you would have to use something else. Like either, if there was a sorting order, look, if there were comparable, the keys, you can use a sorted map, or you can use some other data structures that maintains insertion order, yeah, but not maps.
Okay,
Any other questions? Okay. Yes.
So I don't get what's the difference between a simple linked list that we saw at the beginning of this talk
and
these
sequences?
Yes.
A linked list is by a linked list. The question kind of goes into the definition of sequences versus lists. A list is a sequence. It is a sequence, but there are other types of sequences, not just lists. And I'm going to show you, like in a few minutes, I'm going to show you other types of sequences.
All right.
That are not lists.
Cool, thanks.
But your observation is correct because lists are sequences, in fact. So we saw this. And I want to show you some other things that can be turned into a sequence, okay? We have this function in Clojure called secable, question mark, which tells you if this thing can be made a sequence. So strings are sequences, in fact, returns true. And if we call the function seek on a string, seek is a function that takes something and turns it into a sequence. If we call seek on a string, we get back a sequence whose elements are the characters in the string. I didn't actually show you characters. This is the Clojure literal for a character. It's a regular Java lang character. Okay, and why is this nice? This is nice because it allows us. I think I mentioned it briefly. It allows us to use the same abstractions that the sequence API provides us to work with functions. With strings, so we can use map and filter and any other of the many functions in the Clojure standard library for working with strings. They're no different in any way than, we don't need any special hatch for strings. We don't need anything separate, just map, filter, and anything else, all those other functions. For example, we could take a string and search I don't know why you would do this, but take a string and find out all the characters that are A. You could do this with a simple. Oh, I'm sorry. This would actually. Anyone wants to guess what this would do? This is a good opportunity for you to guess what this would do. Okay. I'm introducing a new syntax here. Basically, this is a string and this is a function. The percentage sign is an argument. It's just syntactic sugar for defining a function with a hash. And so this is a character every time we're looking at a new character. And this is equals. It's like double equals in Java, a comparison equals. And we're mapping. We're using this function to map over this. What? Anyone wants to guess? What? Yes, exactly. Very good. It would return true if the element in this index from the string is A and false otherwise. Yeah, okay. Other things that are sequences. Java arrays are sequences. Make array is a Clojure function that returns a sequence of the type that you get. A Java array of the type that you give it. I'll just show you in the REPL, so you believe me. You see the funky Java notation that you're probably used to for arrays, L and Java long string. So this is an array of size 10, and it's secable, which means, again, that we can use the same abstractions to work with Java arrays, right? If we wanted to create an array of the numbers 1 through 4, and then find out all the ones that are even, we could just use filter. We don't need anything special for working with arrays. They can be turned to sequences. There's one small caveat here is in that Java arrays are immutable. And they're still immutable in Clojure. They're plain all regular Java arrays. So if you take an array and you say, okay, I'm gonna think of this as a sequence, then you kind of have to also remember that some of your assumptions about Clojure go out the door, right? About immutability, because anyone can mutate this array. They're not made mutable by the fact that they live inside a Clojure program. Okay, so when working with Java objects like arrays or other types of Java collections, we still need to be aware of this, that they are immutable, okay? Also, array lists and other Java util collections or stuff that implement iterator are also secable. So we can, again, use map and filter any other functions if you want to work with Java collections. And again, they're mutable, so you have to watch out for that. So you asked before, what is the difference between a list and a sequence? Like they're the same thing. Yeah, so in the beginning, when I first said what a sequence is, I think I said the word logical, that they represent like a logical sequential list of things. And the reason that I said logical is because you don't actually have to have the entire thing in memory. Sequences can be lazy. Okay, you can think of some sequences that are lazy are defined by some function. For example, you might want to have a function of all the integers. I'm sorry, a sequence of all the integers. If you built up the entire, well, you can't build up the sequence of all the integers because you have a finite amount of memory in your computer. But you can have a sequence that is lazy, and as you consume from that sequence, as you call like rest or first, next, 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 it iteratively builds up this lazy sequence. Okay. Okay, so I'll give you an example. I'm going to create a range. We have a function in Clojure called range. It takes a number and it returns you a lazy sequence of all the numbers from 0 to this number minus 1. So let's go to the REPL. And I'm going to evaluate this. I'm going to create a range, call it my range. Its value is all the numbers from 1 until this big number. Okay, and it returned, firstly, it returned immediately. Secondly, if you looked at the memory consumption of this process, it would not change because nothing actually happened here. Nothing happened besides defining a sequence. Right? We didn't consume from the sequence yet, so the numbers, there are no numbers in the sequence right now. As we're going to consume the sequence will be materialized, will be realized, and we're going to get the numbers that we wanted. So just to show you maybe a more visual example, for example, if we take 5, take is a function, is a Clojure sequence function that takes a sequence and a number, returns you the first n elements in the sequence. Then we get 1 through 4. But everything past 4 has still not been materialized. It will be the elements will be realized as our program continues and we take more from the sequence. Okay? Okay. So, 1 second. Does anyone have any questions about this? So, I want to show you an example. So over here, we're going to create a range of 1 through 500, 0 through 500. And we're going to map over it. And the function that we're going to use to map over it just doubles it, x times 2. But also right before it, it prints the number. So just to illustrate the idea of laziness is that, firstly, if I define this, def hello, so nothing happened. And if it weren't lazy, you would immediately expect to see all the numbers printed to my REPL, right? Because the function the mapper function prints them out. But just the fact that nothing was printed from this function, helps you understand that nothing actually happened until I actually consume from the sequence that I received. So now if I use first, which returns the first element in the sequence, if I go first hello, okay, so firstly, I lied to you a little bit because it printed the numbers you can't see, but from 0 to 31, and this 0 is just the return value of first. So the 0 is the first value, but the mapper function, again, I'll show you the mapper function. The mapper function printed out 32 elements. It didn't print 500. The reason that it printed 32 is because map works in a chunked manner. It uses chunked sequences. It's an optimization. each time it realizes 32 element chunk and then proceeds to the next 32 element chunk. So what we did here is we applied the mapping function to the first 32 elements and got back 0. If I call first again, does anyone want to guess what would happen? I'm sorry, if I call first on hello, hello was the range that we defined, the mapping applied to the range that printed out the numbers. I'll show you again. I'm going to comment it out. This is the definition of hello. When we called first on hello, we got back 0 and also print out the 32 first elements in the sequence. What would happen if I call it again? The options are, is it just 0 or 0 and 32, like the numbers printed out to standard out, right? What are you guessing? Just 0, okay. What? The result will be the same, but do you think that they will print out the numbers? Well, you can't really tell if I didn't tell you, but yeah, it'll just print out 0. Because sequences are cached, right? Basically, we have a reference here. We have a var hello that holds a sequence. It's really holding a reference to a sequence, and you can sort of think about it as the sequence is holding a reference to the first element, reference to the second element, third element, and so on. So because this reference exists in memory, it's right here in hello. When we call first, it uses the elements that it materialized previously. So it doesn't have to rematerialize them and do that work again. If we do something like, I don't know, like nth, hello, nth is a function that you give it something and it returns the element at that position. So we could do hello at 32. And then it printed out the numbers again, right? Because this is the second chunk. This is the second 32 element chunk that we spoke about. The first 32 were realized previously, and now we realize the rest. And it keeps going like that, okay? So why is laziness important in functional programming? How many iterations does this, we have, okay, what does this code do? Create a range of 10 numbers. Then we increment them, then we filter them out. So how many iterations happen here? I'm sorry? If I realize the entire sequence, if I realize dual, I didn't tell, dual just realizes the entire thing. It goes through the entire sequence until the end and realizes it. So there are some options, right? 10 is one option. Or you could say, okay, maybe what's happening is first we're creating a range. If it weren't lazy, if Clojure were not lazy, I mean sequences in Clojure were not lazy, then what it might have to do is first create a range, return 10 numbers, then send that to map, or say, okay, now you want to increment them, so I'm going to do that 10 times, go through them, get back, and then send that to filter again 10 times, right? So that would be like, I don't know, 30 iterations, right? That's not the answer. The answer is 10. Whoever said 10 was correct. And because, this works sort of like in lockstep, right? It works lazily. So the sequence from range is materialized, and as we're materializing it, the cause for range to materialize, the reason that it's even materializing is because we sent it to map. Map needs some element. It's telling the sequence, give me something else. And that happens because of filter, right? Filter is telling the sequence from map, give me something else so I can filter it. So we're gonna happen, because it happens in lockstep, right? It would be like 10 iterations, okay, not 30. And that's important because otherwise it would be very, very slow to write programs in Clojure. It would be still like O, big O of n, but the constant inside that n would, the big O would be high. So, if we had to iterate here, according to the number of transformations, it would be very, very slow. So laziness allows us to keep this code working, with good performance, right? Not going through the lists over and over and over again. Does that make sense? Did everyone understand that? Okay, so cool. So now we're going to have an exercise. We don't have very much time left. So what I want you guys to do now is write a function. Does anyone know what the Collatz conjecture is? Collatz conjecture is a conjecture in mathematics that says if you have a sequence of numbers, and the rule for the sequences is you start with some number, that's the first number. If the previous number is even, you divide it by 2. So if you started with 12, next number is 6, divided by 2. And then again you get 3, because 6 is even. If the previous number was odd, then you multiply by 3 and you add 1. So 3 times 3 is 9, plus 1 is 10, then 5, then 16, and so on. And the conjecture says that eventually if you keep applying this rule, no matter what number you started from, eventually you will reach the number 1. Eventually you'll end up with the number 1 here, okay? Eventually it's going to reach 1. So I want you to first write a function that returns a lazy sequence of the Collatz sequence starting with n. And I gave you a hint. The hint is to use the function called iterate. Iterate is a function, I'll show you an example. Iterate is a function from the Clojure standard library which receives an initial value in a function. And it applies the function to the previous value to produce a sequence that a sequence that grows inside. So for example, if a function can be increment a number, and the first initial value can be 5. If we take 10 elements from the sequence that we get back from iterate, we'd get back 5. Keeps increasing by 1 because we used inc, okay? Increment, or we could use a function that doubles fn x times 3. So each element is 3 times bigger than the previous one. So try to do that. And if you do that, I'd like you to write a function that receives, called Collatz satisfiable. It receives an integer and it checks if the Collatz conjecture holds for that sequence. Again, if the sequence eventually reaches the number 1, like here. And for that, I advise you to use another function called sum. Sum is a function that receives a predicate, a function, and a collection. And it tells you, it returns the first element in the collection in the sequence that holds true for the predicate. So for example, my predicate could be a function that gets an element and checks if the element is 10. And then I'd pass it 1, 2, 3, and 10. And it returns true because it went through 1, 2, 3, then got to 10, and it says, okay, it's fine. The predicate holds. So you can use sum. So go ahead, I'll be here if you need help. One thing I didn't show you during this presentation is control flow, or some sort of way to do branching, right? So you might need that. We have if in Clojure, just like any other language. If x equals, I don't know, if true, then that's the syntax. If some expression that evaluates to true or false, hello, otherwise world. So we're going to get this is the first branch of the if, and this is the second branch of the if. So true returns hello. So anything that is true, anything here that is truthy will return the first branch. Truthy in Clojure, falsy in Enclosure is everything is false and nil, and everything else is truthy. So like if you put some number here, it will also this would evaluate to hello. So this is pretty much, I think you should be okay knowing this to do the exercise. If you need help, just raise your hand, please. Thank you. Because we don't have a lot of time, I'm gonna kind of limit it in like, let's say 10 minutes. I know it's nothing, it's the first time you're seeing this weird language. Just do your best. If you need help, call me, and then we'll do it and then try to move on because we don't have very much time left. So maybe we could do this together. Maybe I'll show you a possible solution for doing collats. So I advise you to use iterate. And iterate seems really suited for this purpose because collats is a mathematical sequence that you start with an initial value and you proceed with according to some pure function, right? So one way to do this, for example, would be to use iterate. And the function, what would be the function that you think? Anyone want to say? What function would I be writing here? It's a function that takes an argument and does what? Yeah, exactly. All we need to do is check if x is even, what then we want to, I'm sorry, if x is even, divide x by 2. Otherwise, we want to multiply, we want to increment the result of multiplying x by 3, right? And then our initial value is just n. So if we take this and we pass it to the REPL, let's invoke collats with the number 12. Let's take a few elements. This is, again, this is a lazy sequence, and it's also an infinite lazy sequence, right? Because there's no, it's just numbers. It just continues growing, right? We never mentioned how to stop. It's just we keep iterating through the values. So if we take, for example, 10 from the collat sequence for 12, something is wrong because this needs to be here, I think. Yeah. So, 10 is exactly, I guess, how many elements you need to get to 1 for 12 to call that sequence. If we took a different number like 15, just as a curiosity, you would see that at some point it keeps repeating. There's a subsequence that keeps repeating because when it gets to 1, it's the call-it sequence for 1 itself is 1 for 2 1, and then it just keeps repeating because it keeps hitting 1 again. So we get back a lazy sequence. Now, if we want to know if call-it is satisfiable for a certain number n, we need to check if it reaches 1. So for that, we can just do sum, for example, sum, let's say fn of x is x1. If it is, then we're good. And then we'll pass sum the collats of n. So, okay, so now is collats satisfiable for 12? We know that it is true. Okay, is this understood? And iterate and sum, map, filter, all these functions are just basic sequence functions from Clojure, and you can keep using them. The same types of abstractions for defining different logics, different types of logic, different types of domains, you keep using the same set of abstractions that the language provides, okay? For working with sequences, for working with data, and so on. Okay, we're gonna skip these. I wanted to show you a little bit. How many people here work with Java in their day-to-day? Or something that runs on the JVM? Almost? Like half? I expected more. Okay, so Java, interop, Clojure. We said one of the main reasons that we like Clojure at AppsFlyer, and I like Clojure, is because it's also a practical language. It runs on the JVM. It has full access to the ecosystem. It has full-time access. It receives the benefits of the runtime that we like when we're writing Java applications. And part of the thing that we need to leverage that is interop with Java, with the rest of the Java code that exists in the world. So Java interop in Clojure is really simple. As an example here, we're defining SB. It's a string builder. The dot is a constructor. This is the way you call a constructor. A constructor, it just looks like a function invocation in Clojure. You wrap it in parentheses, but all you have to do if it's a Java constructor, you just add a dot at the end, creates a constructor. And to invoke methods, method invocations also look like function invocations, except you add the dot at the beginning of the method's name. So instead of writing sb.append like you would in Java or some other language, you do .append, the first element being the receiver of the method, like the object you're invoking on, and then arguments. So here, if we take a look, and again, everything holds. String builder, just because we're writing in a Clojure program, it's the same exact string builder, and it's mutable. So if you're doing Java interop, you do need to be aware that some of the assumptions that you have when you're writing pure Clojure code don't necessarily hold true. For example, here, if we're defining a string builder, take it to the REPL, and then we do this, then we evaluate the string builder, we see that it has a low, and if we mutated it, we mutate it, then that mutation takes effect, right? There's an effect here that happens, even though Clojure is immutable. The immutability of Clojure holds for native Clojure constructs, data structures and sequences and so forth, not for anything else. Static method invocations look like this. You just you just prefix the method name with the class that holds the static method. So, for example, if we wanted to parse the number 1, 2, 3 into an integer, we would do this and get back an integer. I want to touch briefly, because it's sort of, it's part of the Clojure philosophy. So I want to touch briefly on how we deal with modeling data and polymorphism in Clojure. So one way to model data in Clojure is with records. Def record, something, and then a list of some, you can think of it as fields. This construct, Clojure records, this is a Clojure construct, compiles to a Java class, right? So this would actually compile to a class called color, and in the bytecode for that class file, you would have fields R, G, and B. Okay? And then to create an instance of this class, you use this notation of arrow, name of class, and then some arguments you pass to the constructor. Okay? So we define a color with this RGB value. Okay. So this is basic way for modeling data. It's sort of similar to what you may be used to. If we invoke it, we get back a color. But usually when we model stuff in Clojure, we use the intrinsic, the native Clojure data structures. We usually model different domains using the exact same of data structures that Clojure provides us, namely lists and vectors, maps, and sets. So usually to define a color, if you had this domain that needed something like an entity called color, usually what you would do in most Clojure code is just use a plain old map whose keys are the names of the fields and the values are whatever the field holds. So you would usually see something like this rather than like this. This still has, we still use records, but usually the modeling of entities is just uses regular data structures like this, and it's nice because it allows us to use the same abstractions that we're used to when we're working with other types of data, because everything is data. Then different domains that have different types that model themselves with data always use the same abstractions from the Clojure library. So for example, what I mean by this is imagine that you had a list of people. So in Java you would have a class called person and have a name, have an age. In Clojure, what we usually do, we just treat it as data, right? We say if we want people, what is a people? A people is a list or a vector in this case, and each person is just a map. There's a name, has an age. And because it's just plain data, we can use the same abstractions that we're used to in the Clojure that exist in the Clojure API to work with them. For example, if we wanted to sort the people by age, and then after we sorted, we wanted to make the change the name to uppercase. All that would be, because people is just a list of maps, would be just, we would call a function called sort by, which is a Clojure function that receives some sort of comparator for sorting. Remember that age, not a comparator, but it receives a function that it calls that function on each element to get something that's comparable to each other. So remember that a keyword in Clojure is a function. And when you invoke a keyword on a map, you get back its own value in the map. If I do something like, if I take one person in here, like I take this one, and I use the keyword age as a function, and I supply it to the person, I would get back its age, right? So we can just call sort by with age as a function, and then we can pass that new collection to map, and it's just a map of maps, right? So we call a function called update, which takes some map, some key, and some function to update the value for that key to some other value. So here we're mapping over the people, and each time we're mapping, each time we get a new person, we just change its value in the map, the name for that person, we just change it to uppercase by using the function uppercase. So we use data to model almost everything. I mean, HTTP requests are maps whose keys are the status, and then another key who's the headers, which is by itself a map of the headers, and the response usually in the Clojure web apps would also be a map with a key for the status and the body and so on and so on. Okay. So, but this is usually how we model data. We also have something called protocols, which are like Java interfaces. We can define a protocol. For example, here we're defining a protocol called countable, which has a method called countit, who receives some argument. The argument would be like this in Java. Okay, so we're defining a protocol. Let's think of it as an interface that has one method, and then we can extend different types to use this protocol, okay, to achieve some sort of type dispatch-based polymorphism. Basically type dispatch, right? So we can even take classes, just regular Java classes like string, and we can extend the protocol to use them. For them to implement the protocol. So for example, we can extend string and we can say, oh, the implementation for countable for string is just how many characters, the length of the string. So this does not work because and then now if I wanted to, I could do something like this, count it, hello Devoxx, and I would get back 13. Or I could extend this protocol to some other type like color that we defined previously via a regular record, and then just say the count it for a color is this weird definition where it adds the RGB values together, sums them up. And then I could do count it for some color. So records and protocols allow us to do type dispatch Enclosure. There's another mechanism which is very different from this, and I did not go into it, which is called multi-methods. This is a very different approach to polymorphism. It's really interesting if you want to read about it. And the last thing, I think someone had a question before. I think you did about state, right? You asked me, so how do you do things if you can't? If all data is mutable, how do you change? How do you change things? Or maybe you had a question about side effects. But another question, it's sort of in a similar fashion, would be to say, okay, if you cannot change data, sometimes you need to change something, right? You have some global state in your system or in your program that needs to change. If you cannot do that, then it's hard. Hard to achieve any interesting program, how to write it. So the last thing that I'm going to show you is Atoms, which is a Clojure concurrency primitive. Clojure comes with several concurrency primitives. The one that I'm decided to show you is Atoms, but we also have stuff like agents, which are similar but not exactly like actors in other languages. If you've ever used something like the actor model, we have something called refs, which implements some sort of software transactional memory, in which different threads can sort of open a transaction in which they modify some data in memory, and if we discover sort of a collision, then the transactions can restart. But the last one that I wanted to show you was Atoms. Atoms basically you can think of them as sort of a container that holds some data inside it, and you can change the value of you can change whatever is in the atom. The data itself inside the atom is still immutable. You can just tell the atom, okay, you used to hold this, I want you to hold that now. And inside when you call, I'll just show you. So let's define an atom that holds an empty map, and then we can call a function like swap, the function swap, which takes the atom and also takes some function that receives the value of the atom, the value inside the atom, the map, and then applies some function to it. And that'll be the new value of the atom. So if I evaluate this, then I get back a new atom. I mean, I'm sorry, I don't get back a new atom. It's still the same atom, just with a new value. The function swap just returns the new value. If I look inside the atom, if I look, the @ sign is just a way to dereference the atom to see what's inside it. If I dereference the atom, then I see that the value inside the atom has changed. Okay? But what's important to understand here is that while the value of inside the atom has changed, the map itself is still immutable, right? The map that I started out with is immutable. We didn't change this map. We just applied a function to the map to get back something new. That's what's in the atom now. Inside of it, the way that it works is basically via a cast loop. It holds an atomic reference. So when you're doing something like swap, it basically does a cast loop in which it keeps casting with the function, and it keeps doing it until it succeeds. So if two threads want to change the value of the atom at the same time, one of them will succeed, the other one won't, because it does it via an atomic reference. So one thread will succeed to do the transformation. The second thread won't succeed because it's an operation, and then retry until it does succeed. And it's a nice concurrency primitive. It's basically, you can think about them sort of as atomic references that come with some nice functions to work with them, but it also allows us to sometimes have like state in our program. For example, we could put inside the atom some global state that different threads need to modify concurrently over time. Okay, that's it. I think we're out of time. Thank you for coming. I'm sorry it was kind of short. And I really do encourage you. It's really an interesting language, and there's a lot more to cover. There are a lot more facilities for concurrent programming and asynchronous programming that come with Clojure that we use at Abstract all the time. Like I said, we do something in order of 90 billion events every day, and we do it all with this language. So we're very happy with it. And if you are interested, we are also hiring. We have an office in Kyiv. So if you want, go for it. Thank you.